I'll give you one more minute. All right, so first two are indefinite, so we just want to find the most general antiderivative. So the 3 comes along for the ride. Anti-power rule, add 1 to the power, divide by the new power. 4 comes along for the ride, add 1 to the power, divide by the new power. Antiderivative of 5 is 5x. Always add a plus c at the end. So of course you could simplify those constants out front if you want a little bit to get this. For the second one, this is technically a 3x to the negative first, so that's the only situation where we don't use a power, anti-power rule, if you will. So this is going to be the natural log situation. So we have 3 times the natural log of the absolute value of x, because essentially the 3 just comes along for the ride, and then the antiderivative essentially of the 1 over x is natural log of the absolute value of x. 2 comes along for the ride. If you're in an e to the kx situation, you have an e to the kx. But then the antiderivative rule says we divide by that constant or multiply it by in fraction form in the front, plus c. So if you want to clean that up just the tiniest bit, that would be 1/2 e to the 4x plus c. Questions about either of those before we do the definite ones? Okay. So the definite ones, remember, essentially start in this where we have to find the antiderivative first. So the 4 comes along for the ride, add 1 to the power, divide by the new power. 2 for the ride, add 1 to the power, divide by the new power, plus c. But we're going to have to include our bounds. So let me clean this up a little bit first. Oh my goodness. X to the 4th plus x squared plus c from 0 to 2. Top bound minus bottom bound. So you plug in the top bound first. Subtract what you get when you plug in the bottom bound. 2 times 2 is 4 times 2 is 8 times 2 is 16. So 20. And yes, I know you can type those into your calculator, but I'm expecting you to show me the antiderivative and the answer. Oh, sorry. The number over the x, you always... Yeah, Kayla, so if it's ever... so scroll back up really quick. So this is essentially equivalent to 3 times 1 over x. So if there's ever a number above the x, that essentially comes along for the ride. And then it's technically just the antiderivative of 1 over x that gives us the natural log. So yeah, whenever there's a number up top, it just kind of tags along on the outside. And then this last one. So this one was kind of one of those ones that I said in Wiley you definitely have to do by hand because it wants the exact answer. So here the 6 comes along for the ride. We get e to the 3x, and then we have to divide by the 3. Antiderivative of 2 is 2x. 6 divided by 3, so 2. Yeah, sorry. J, x to the power of something. Yeah, so J, whenever you have x to the n our anti-power rule says, yeah, you add 1 to the power and divide by the new power. Exactly. I didn't need to erase that so soon. Sorry about that. So I've got my antiderivative. I'm going to plug in my top bound, so 2. So everywhere I see an x, I'm going to, whoops, I'm going to put it, I'm going to subtract what I get. I'm going to run out of space. When I plug in 1, because I don't think I ever did this out in full generality because I'm just so used to it happening in my life that I forget. So here, technically what happens, we have the 2e to the 6 minus 4 plus c minus 2e cubed plus 2, because we have to distribute the negative, and then minus c. So the c's always ends up canceling each other out. I think I mentioned that, but I don't think I've ever written it out fully. So that's why the c's always disappeared, because when you distribute the negative, you end up with c minus c in absolutely every definite integral you'll ever calculate in your life. So here, I would honestly leave it as, I would just simplify the negative 4 and plus 2 to give me negative 2, and I would just leave it like that. How do you put it into Wiley? Like this? So if you were trying to type this exact answer into Wiley, you would want to even put the 6 in parentheses just for, so in this case, the parentheses wouldn't really do much. But say you were trying to type in a, I don't know, e to the 1/2 for some reason. If you don't put parentheses around that exponent, it's not going to accept it. So make sure, even for maybe the silly cases, putting those around should help. But it should just be 2e caret 6. I think sometimes they have the option for the equation editor, and that should probably have like an e to the x button. But it should also accept that kind of notation as well. Kayla, I got the 2e to the 3 times 1 because I needed to plug in my bottom bound of 1. So I plugged in my top bound first, so I plugged in a 2 everywhere I saw an x. And then we have to plug in our bottom bound, so I have to plug a 1 everywhere I see an x. So since there was an x here, it should be 2e to the 3 times 1. Oh, you said never mind. Victoria, so this is, I ran out of space. Let me come over here really quick. So if we go from this line, we have 2e to the 6, whoops, minus 4 plus c. But notice this negative in the front here, we have to distribute that. So we have minus 2e to the 3. But then since this was a minus 2 times 1, when we distribute the negative, it becomes a plus 2. So that's why it turns out to be negative 2, because the 2 in the back needed to change to a positive when we distribute the negative. If that negative doesn't get distributed, then yeah, you will end up with negative 6. But that's incorrect because we need to make sure we distribute that negative to that second piece. Juliana, in terms of Wiley, no. So Wiley would need this. In terms of the quiz that you're taking today, and even if you take it online, what I'm expecting to see is so I've completely butchered that side. So let me, on the quiz, I'm expecting you to show me the antiderivative, and I want you to at least show me you plugging it in. That's not very, picking that up a little bit. But after that, if you just want to punch it into your calculator, that's perfectly fine. So on your quiz, as long as you showed me the antiderivative and the plugging in step, if your final answer was a number, that's perfectly fine. Does that make sense? Hopefully. So I do want you to show me the antiderivative, show me you plugging it in, but if your answer turns out to be a number, totally fine. Yeah, Kayla, you can send me your work for the quiz again for this one if you want, just like last time. So, okay. Questions, concerns? I know I did go through that a little fast because I'm flustered, but if you have any questions, if you want me to go back to one of the other ones, now's the time to ask. We are kind of going to be doing a bit more of this in the notes today. today because the stuff we're doing today still includes integrals. So yeah, so you're going to have two, essentially the same kind of setup. You'll have two indefinite and two definite integrals to calculate. So Kayla, if you send me your work, no, but just in case someone's not sending me their work, make sure you're including that in the space on the quiz on Blackboard. But if you send me your work, then you can just type in the final answer into Blackboard. All right, I've got to pull up our notes because I had to run to my office, so I don't have them up yet. So we're talking about 5.3. 5.3 is about the integral as area. So remember, we kind of found that we calculated like two integrals and one of them turned out to be negative. So then we found that any area that ends up below the x-axis when calculated in an integral is going to end up being negative, considered negative. And then we asked the question, okay, well, what if we want to figure out what the total amount of stuff there is? And actually, before we get back to the official, I kind of want to come over here really quick. Nothing's shared yet. 1 second. Let me come back here really quick before we get to our official notes. So it should be up now. I just shared it. There wasn't anything shared about a second ago. If you can't see it at this point, let me know. So there's kind of two things we're going to talk about at this point. We're going to talk about total area, and we're going to talk about area between two functions. And you can actually use the same process for both. And we like barely started looking at the process the other day. I want to explain it a little bit more before we jump over to the official notes and write it down. So essentially what's going to happen is, suppose you have two functions. Here's an f of x and here's a g of x. I don't like that. Let me draw other ones. And let me do colors here. So say we have some function f of x, and say we have some function g of x. And say I asked you to find the area between these two functions. So essentially going between, let's call this a and let's call this b. At this point in time, we only know how to calculate a single integral, right? So if I were to calculate the integral from a to b of f of x, remember that finds me the area underneath of f of x. So if f of x is my green function, the area that is going to find, so let me get rid of these lines for a second. What is that? So I'm going to draw horizontal lines for this area. So that area will actually be all of this area in here. The area underneath of that green function, that would be the integral of f of x. And then if I were to calculate the integral of g of x, let me shade that area with vertical lines. That would end up being the area underneath of that line. So all of this area in here. So notice that there's a little bit of area kind of in the middle, if you will, that's only the vertical lines. And then there's area at the bottom, which is both the vertical and the horizontal lines, right? And I only want the area that's only the vertical lines. I only want that area in there. So essentially, you can think about this red area as essentially taking the entire area given by g of x and subtracting off the area from f of x. Does that make sense? So essentially, if we have all of the vertical lined area and we take out the piece that's also the horizontal lined area, we're left with the area I actually wanted. All of that to just show you why what we're going to do works. Now remember, we can split up integrals. If we have the integral of f of x plus g of x, we can split it up into the integral of f of x plus the integral of g of x. I can also go the other way. So I can essentially smush this together to be this. I wanted to do this so that the process that we're about to write down will hopefully make a bit more sense now that you kind of hopefully see why it works. Notice that the f of x is below the g in the area that I'm caring about. This is going to be what we call our bottom function, and this is going to end up being what we call our top function, because in the area that I care about, g of x ended up above f of x, okay? So all that to say, now we're going to jump over to the official notes and write down the official process, but that's kind of why it works. Why we're kind of looking at this integral of a function minus another one, because we want to take a certain area and take away another set of area to left with the area between the two. Now again, this process is also used to find the total area of a function between the function and the x-axis. So just, this isn't a function and the x-axis, this is two completely separate functions, but the same process is used when you have a function and the x-axis. So jumping over to our official notes, why doesn't it let me share the things correctly today? Anyway, zoom in. So we barely started talking about this the other day. So this is kind of exactly what I was just getting at. So to be able to calculate the area between two functions, which again can also be used to find this total area idea, you find where the two functions intersect. If you're looking at total area, your second function is y equals 0, the x-axis. You're going to split up the interval, if necessary, I should be clear. So let's say that if you set those two equal to each other, let's say you get x equals, nope. Let's say you get x equals c. And let's say you're going between two values and c is in the interval that you're going between. We'll do an official example in a second and hopefully it'll make more sense with actual numbers. But essentially, if you're going from a to b of whatever you're integrating, and this c value is in that interval, what we're going to do is we're going to split it up at that value. The reason we have to do that is because sometimes the functions will switch which one is on top of the other. So in the picture I was just saying g of x was above f of x in that entire interval, but if I went past that interval at all, it would have switched. So that's why we sometimes have to split it up, because we have to keep track of which one's on top of the other, and sometimes they flip-flop. If you're not given an entire interval, say you're just looking over x is greater than 0, or you're not given an interval at all, you form intervals using the values that you find when you set them equal to each other. So obviously you'd have to find 2 or more, but if it's a question that should work that way, then you will find 2 or more where they intersect. You're going to then look to calculate the integral. Now don't get super bogged down and I'm switching back to a to b. I just have to be generic. You're going to find top function minus bottom function. So that's why I noted the top and the bottom in the thing we were just talking about. To find which function is on top of the other, you essentially have two choices. You can either graph them and just look at it. Is higher than the other one. Or you can choose a value that's between the two bounds you're integrating between, plug that into, it's almost like when we were doing the first derivative number and you had to choose a test point to see if it was positive or negative. It's kind of that idea. You pick a test point in between the 2 points that between, plug it into both functions, the larger y value is on top. We're going to do official example in a sec. Now I'm going to skip writing it formally for the sake of time so we can actually get that example in because we're already running out of time. Wednesdays are great. So I'll leave that up for a couple more seconds in case people are writing anything down. And then we'll do one formal example, and then we'll do a lot more on Friday. So at this point in time, it looks like you're only going to cover up to 5.3. Well, I should be careful with the phrasing. 5.1 through 5.3, and then 6.2 and 6.3. So the antiderivative stuff we did, but then I was hoping to get to 5.4, but it doesn't seem like we'll get there. That's okay. Anyway, so we'll write it down formally on Friday. So let me look at this first example, example 3. Find the total area for x cubed on the interval of 1 to 1. So again, yes, you have a test next Wednesday. Oh yeah, did I mention that? All right. Did I mention that on Monday? You have a test next Wednesday. Just like last time, I'm expecting you to take it in person. If that's going to issue, you need to let me know ASAP. If you want to take it with the disabilities office, please sign that up ASAP so that they can accommodate you. But yeah, next Wednesday is your last in-person exam. Also, if you would like to, instead of coming to a classroom full of people, you can come to my office and take it separately if that's part of an issue for you. If you just don't want to come to a class full of people, we can set that up. Email me. Anyway, let's do this. So notice that this says total area. So again, this is kind of that second type of problem that we can do with this process. So essentially the second equation we're using is y equals 0. So we're essentially finding the area between y equals 0 and y equals x cubed. That's why we can use that same process. Even though it's not phrased as find the area between these two functions, that's essentially what we're doing. So if you write very large, be a little careful because I don't think I gave us enough space for this if you're writing on my sheet. So the first thing we need to do is find where they intersect. So we're essentially setting y equals 0 equal to y equals x cubed, so x cubed equals 0. If you cube root both sides, you'll get that x is 0. So that's where they intersect. Notice that 0 is between 1 and 1, so I actually care about it. Like some of the other things we've done, if that number is outside of the interval, you don't care about it. But since it is in that interval, we need to care about it. What we do with that is we're going to need to split up the interval. So essentially, we're now going from -1 to 0 and from 0 to 1. So we're going to be calculating integrals from -1 to 0 of something. So just to show the notation, we're going to pop up in a second. So we'll essentially have to do two different integrals. One between -1 and 0 and one between 0 and 1. If there was no place where they intersected in that interval, you would just be going from -1 to 1. So use the given interval, and if necessary, split it up. We now need to talk about top versus bottom functions so that we can actually set up the integrals that we need to calculate. So, oh, good question. She asked, how do you know which one's the top one and bottom one for, I assume, the bounds on the integral? The smaller number is always on the bottom. In general, things can get a little weird, but in terms of our class, smaller number is always on the bottom. Now I'm going to show you both ways for this, the graph way and the kind of algebraic way. So the algebraic way, we have these two intervals we're working over. Just like with our derivative number lines, pick a number in each one of those intervals. So I'm going to pick negative 1/2, and then positive 1/2. You're going to take that value you just picked. It shouldn't matter what number you pick as long as you've done everything else correctly. And plug it into both functions you're working with. So we're working with y = 0. Well, there's nowhere to plug anything in there, so we just get 0. If we plug negative 1/2 into x cubed, we're going to get negative 0.125, or negative 1/8 if you prefer. Which number is larger? 0. So that's going to be our top function in that interval. So y = 0 is going to be our top function for the first integral. And then I'm going to plug in positive 1/2. So if I plug it into y = 0, again, where to really plug it in, so we just get 0. If I plug it into x cubed, we're going to get positive 0.125. Oops. What's the larger number between those two? 0.125. I'm running out of space. Let me zoom in a little bit real quick. If you were to graph this, it would look like this. And essentially, if you stop it at negative 1 and positive 1, you'd essentially be looking there. So if we're splitting it up at 0 as well, notice in that kind of left side, the x-axis is above the function. So the x-axis is on top. And in the second interval, the function x cubed is on top. So you can also do it graphically if you prefer. All right, I'm going to set it up. We'll come back to this a little bit on Friday because I'm running out of time a little bit. So we have 2 intervals that we're working over. And the integrand is all top function minus the bottom function. So in the first integral, the top function was 0 and the bottom function was x cubed. Oh, sorry, that just must have popped up right super. Yeah, Jackson, so the negative 1/2 and positive 1/2, exactly what Kayla said. I have 2 intervals, negative 1 to 0 and 0 to 1, and I just picked a point in those intervals. Think about when we were doing those first derivative number lines, and we had like those spaces, and we had to pick a number in each piece. Kind of the same idea. So I picked a number between negative 1 and 0. I just chose negative 1/2. You can choose whatever you want. Between 0 and 1, I chose positive 1/2 because that's what I chose. In the second integral, the x cubed function ended up on top. So we get top function minus bottom function. I know having zeros in there makes it seem a little stupid, but when it comes to be a function that's not y = 0, it really does matter. Well, it matters here too, but I know writing minus 0 sounds a little dumb. At this point in time, for these types of questions, at this point you could just punch them into your calculator if you wanted. You can, of course, do them by hand as well. But for these, they're so long in the first place that at this point, just plug that sucker into your calculator. You are going to need to know how to do them by hand, but I will ask you those as separate questions like we did on the warm-up. I'll come back to the final answer for this on Wednesday, you know what I mean, Friday. And we'll talk about this a lot more on Friday. I know it's a pretty hefty process, kind of like the max-min stuff with derivatives. So we'll come back to this on Friday and probably on Monday as well a little bit. But at this point, the quiz should be up on Blackboard for y'all on Blackboard. If y'all can put up your